Okay, I have great pleasure to introduce Walter Jehne. Now, Walter is an internationally recognised soil microbiologist, so thank you, Phyllis, for such a fantastic introduction. He's also an innovation strategist. Now, Walter has an immense field of research and experience in soils, grassland, agriculture and forests. Now, he's done this at a local level, a national level, and there's some citations here from Australia at both a national and federal level over there. Walter has a remarkable ability to explain complex science and economic paths forward in an easy to understand way. This comes in part because he's also worked extensively beyond science at a federal government level, leading transformation in industry and policy. It's this rounded out diversity of experience that has given Walter a unique and exceptional capacity to devise solutions and turning challenges into opportunities. Walter.
Thank you very much. Okay, well I can do that. Okay. Well look, thank you very much, Peter, and thank you very much, Phyllis, and most importantly, thank you very much for coming and listening, but also having the discussion, because I think Peter's been very provocative this morning. There's very good questions, very good issues arising, and I think it's really powerful to kick off a critically important discussion. I'd also like to thank Phyllis, because my colleague Didi Pershouse, and we did this flour and bread thing for primary school children, right? Because it's all about pedogenesis. What actually created soils on this planet 420 million years ago when I was a bit younger, and really what was the thing that actually enabled soils to form, and of course ecosystems to grow from those soils, and really get the understanding that it was, yes, the yeast, the life, the microbial gluing together of that raw material, that flour, that actually created structure, and it's out of that structure that life and prosperity and profitability and viability extends. And instead of just having a dead, inert mineral mass and losing resources, you saw that water running off. The key question there was, yes, the lack of infiltration, the lack of that water, that critical resource. Water is life, but that life was running off. Instead of that, of course, that water resource was being conserved in the bread, and in a sense, that's exactly what soils do. So we started off with, young school kids, but then we had a whole lot of meeting in Chicago with stockbrokers and venture capitalists and what have you, and say, how do we get this message to them? And hey, they loved it, you see, but they didn't want to eat the bread afterwards. That's okay, soggy story. But thank you very much, Phyllis, and in a sense, we'll be going over some of those key messages of actually, soil microbiology, pedogenesis, life, but particularly coming into agriculture, and then perhaps addressing some of those issues that Peter raised as far as, well, where is the future of agriculture? And it all, of course, starts with us. At the moment, there's 7.5 billion of us on this planet, not just 40 million rich people, right? 7.5 billion people. We project, UN, etc., project 10 billion people by 2050, 30 years' time. 8 billion of those will be living in cities, okay? And so they become extremely dependent, but also extremely vulnerable to, of course, air, water, food, habitat, climate, social stability. Critically important. We had a pretty unnerving experience, 12 years ago, the Arab Spring, the reality that there are 7 missed meals between social stability and chaos, collapse. We have 8 billion people in cities, 7 missed meals. We last for 3 minutes without air, 3 days without water, 7 missed meals, food. Normally we can go for about 3 weeks, but social stability, vulnerable, 7 missed meals. So basically, this has really concentrated the mind of a lot of people, and sure, we can have police forces, but crowd control don't stop 10 billion people without food. And so the real issue is how do we actually provide the habitat, the resources, the food, the water, the air, the future, not just for 40 million, but for actually humanity. And of course that's become the real focus in the UN context. Okay, we've been there for 50 years, talking, debating. We've known about these issues. You know, when I graduated, hey, here's the limits of growth, here's climate change, healing, etc., etc. All the issues have been there, but basically we haven't addressed them. We've talked, we've spent 80 billion US on an IPCC process and modelling and what have you, but basically in December last year, Fizz in Madrid, no solution, basically gave up. Everybody can do their own carbon accounting, so even what we had achieved in Paris, 2015, the whole target of zero net emissions, a bigger agenda of, okay, we have agency of drawing down, of managing carbon, goes out the window because each nation can do what they like, can do the accounting on their own standards, which means nothing. And so Antonio Guterres, the Secretary General of the United Nations, recognising this is serious, but also that there's no solution, called together a special conference in September and basically said, hey, what have we got left? You know, what are the actual options? And the bottom line and the agreement was, yeah, look, are there still, I mean, we know there are, these natural climate solutions, these natural bases of doing things, the grassroots uprising, revolution of communities, farmers, growing, rebuilding, regenerating ecosystems, because at the end of the day, you are the solution. Okay, it's farming, land management, rehydration, regeneration, regional revitalisation. That's the bottom line, not just 40 million rich people. Okay, and so that becomes a key game. And New Zealand's a little country in the Pacific, you all know that. And basically your Prime Minister then stepped up and took a lead, and with Macron, French President, sort of sat down and say, okay, well look, what can we do as a small nation to provide efficient, sustainable, reliable, quality in a global food system? Of course you're not going to feed 10 billion people, but the point is what can you do with leadership, demonstration, innovation, really saying, yes we can, there are ways to get forward. And it's really, that is the human enterprise, isn't it? It's here's innovation, here's excellence, but also here's nature. Because all these solutions are there in nature. And it's really us picking up that natural opportunity, that natural solution, putting it into our framework and saying, yes, we can. And so really, that's the game that we're here, okay? Now, we hear a lot about regenerative agriculture. We've got to be very, very careful. It's a wonderful fig leaf, you know, all the politicians buy it as a fig leaf. But we've got to go deeper. We've got to get into understanding what are the processes behind it and how do we use those processes to actually regenerate, rehydrate. And in a sense, Dee and I, when we're putting that flour sponge bread statement together, that's in a sense what we're doing. But as in nature, it's extremely simple. I mean, nature is very, very raw, basic, simple. You know, she's got sunshine, she's got CO2, she's got water, she's got nitrogen in the air from above, and she has stardust from below. Soil, mineral elements, you know, 96 natural elements of the periodic table. And that's all she's got. So how does she actually build life, biosystems, viability, futures, joy out of that? And of course, what do we do to see that, to respect that, and actually take that forward ourselves? Okay? And that's what regenerative agriculture is about. Not, you know, I'm doing zero till or that. I mean, there's no question about that. But really getting to the guts of it, because that's what it's about. And as we sort of said, and as we showed, and as Phyllis showed in that little bread example, that's the starting point. So, I basically mainly talking to farmers, and so often farmers, I mean, it's a nightmare electronically, so we often just like going back to simple diagrams and whiteboards, right? Because then it's all very, very logical, simple. Now, if I put this here, can most people see? Most people see? Hello, can you see okay? Good, thank you. Right, and it's really pedogenesis. You know, it's really starting off, as we said, Mother Nature, what has she got? Sunshine, CO2, water, nitrogen up there. Very important point, we'll come to that later. Nitrogen's all up there, 78% in the air. Triple bonded together to be stable and out of our way. But we'll talk about that later. It's pretty important here in Lincoln, Canterbury, etc. But what did nature do? Okay, she basically sort of had all these resources, and then she had stardust. And stardust is, in a sense, in the form of rock. And of course, there we've got our silicon and phosphorus and calcium and magnesium, you know, all the 96, or not all the 96, but most of the 96 elements in the periodic table. And of course, that in itself is, an earth rock. It's got a bulk density, depending on its minerals, of 2.6 to 3.5 grams per cc. So it's, weight per unit volume. But when we put a drop of water on that, a bit like Dee Dee's demonstration, obviously that water runs off. And of course, that's no basis for life. So 420 million years ago, we're in a situation where basically we had oceans and there was rock, but all the land was dry, arid, bare rock. Okay? There was life in the oceans. Life had evolved 3.8 billion years from now, or previously, so there was life in the oceans, and that life depended on nutrients leaching from that rock, because obviously nutrients became the limiting factor to that life in the oceans. And because life has got some gutso, some competitive advantage driving it, there was a real competitive advantage is, can I get onto that rock to solubilize nutrients? And of course, straight away, life did just that. So it took fungi, because they're membrane tubes, growing from the estrine edge, growing onto the rock to basically solubilize nutrients. Okay, because that's a competitive life force. But again, another important lesson, fungi are basically proto-animals. This comes back into Peter's feeding the world with protein perhaps. Fungi are proto-animals. They can't photosynthesize. Okay, their biochemistry is very, very close to ours. Okay, so what they have to do, and this is Lynn Margill, this sort of stuff, they had to sort of take some mates on, as you would, you see. And so basically what they did is said, look, here's some blue-green algae. There's blue-green algae in the ocean, so I'll take some blue-green algae along and I will make some lichens. And lichens, of course, are symbioses between fungi and algae. And of course, you also know lichens in New Zealand because they're the things that are eating your rocks, your timbers, your concrete, your parked cars. Okay? That's their business, solubilizing rock or solubilizing nutrients, organic acids, and of course, breaking up rocks. And of course, what then these lichens do, and the plants that grow from them, they will actually create organic detritus, which is exactly these mineral particles, phosphorus, calcium, silicon, iron, etc. Okay, they'll have these mineral particles, but instead of it being all tightly together, they actually create the Earth's soil carbon sponge. And how they do that, they just leave behind organic detritus. And to be figurative for everybody, we can think of them as bed springs, right? Because that makes the sponge analogy too. But basically, if we put about 3% carbon into that soil mixture, and the carbon is just the dead detritus left behind from the fungi, when they grow and move on and they leave behind their cell walls. Their cell walls are made of chitin, glucosamine, which then dehydrates down to a compound called glomalin. Okay? So you end up with these 3% carbon matrix. But now you've created something profoundly different, because basically if you look at a bulk density of an organic soil, you're looking at something like 1.2 grams per cc or less. So you see that what nature's done, she's basically created these organic sponges by adding nothing. Okay, so the thing that makes healthy soils is nothing, just air. Okay, so if you want to make healthy soils, go to the shop and buy some nothing, but don't pay too much for it. Okay, because now we have actually profoundly changed the physical structure, and this is really important. This is a bit like what we saw in the bread, isn't it? We have changed the physical structure. But in changing the physical structure, we also fundamentally change function and properties. Okay, because now when we put a drop of rain onto that sponge, as Phyllis so elegantly showed us, what do we have? We have infiltration. But more than that, we have in-soil reservoirs. In-soil reservoirs, right? The capacity to infiltrate and make water available over long periods of time from these soils. Okay? And water is life. You're farmers, you all know that, hey, hang on, you're in New Zealand, you always get rain. In Australia, we haven't had rain for 18 months. Water is absolutely critical. Okay? So the capacity to infiltrate and retain water in our in-soil reservoirs, fundamental. What nature's also done in this game, again, more profound, because here we've got basically all these nutrients, phosphorus, calcium, magnesium, etc. But of course they're all unavailable. They're all locked up in a mineral matrix. You can't get to them. So they're in the reserve bank, they're there in your total analysis, but they're not available. But of course, once you create the sponge, guess what? All of these surfaces are exposed, right? So all of a sudden, our nutrients, the availability of those nutrients goes up profoundly, exponentially on a surface area, pi to the cube. Okay, so we've got a massive increase in biofertility. But we have an increase in biofertility, again, by adding nothing. By just changing the physical matrix. Okay? So we have, in a sense, moisture, we have nutrients. And of course, they're the limiting factors for plant life, for life. So, in comes the next guy. Okay, if we then have a black, let's do black, well, no, blue. See, if we have a root growing into this thing, what will happen to a root growing here compared to a root trying to grow into that? You see, a root trying to grow into a rock doesn't do too well, and so you end with a compacted, it doesn't have to be a rock, it could be a compacted, sort of subsoil, but basically you end up with a very restricted soil strata matrix. 20 centimetres of soil colonization. Here, nature goes down to 3-4 metres, easily. So the volume of soil resources that you are now basically accessing, or life is able to access, is profoundly increased. And so we have water, we have nutrients, we have soil resources volumetrically, enormously. Goes further. If we now look at microbial life, okay, this was dead, inert, now we have habitat. So we have basically living surfaces, voids, substrates, and we have basically a proliferation of microbial life. There's 10 times the biomass of life that we're standing on compared to above the ground. You know, the biomass of living microbial life in the soil, healthy soils, tenfold above the ground. And all of that is, in a sense, functioning, solubilizing, fixing, accessing, uptaking, cycling nutrients and the bases of more productive life. So the microbial ecology in these things goes up, again, exponentially. And of course, as Phyllis mentioned, you see that's where our disease resistance, you know, our capacity to basically buffer and control diseases is all just neutral. The immunological capacity of that soil goes up enormously. So really what we're saying is just through this simple creation of the Earth's soil carbon sponge, we put the foundation, nature puts the foundation for productivity and resilience. And it's profound. You see, and in a sense, we can do this as well, very easily, because all we have to do is add bed springs, right? Add some carbon. Okay, so it's not an ETS, it's not how many tons of carbon I can draw down, but it's the actual functional relevance of that carbon in driving soil structure. Okay, and it's only 3%. I mean, basically every little bit extra helps. You only have to be at 3%. Now, every bed spring helps effectively, right? So it's not the quantity, it's the functional effectiveness of that carbon you're adding to soils. So really, it's quite wonderful because it's that easy. Now, then the question is, okay, well, if we know this is how soils work, how do they solve the problems that we're facing in agriculture? And of course, the problems vary from place to place, different priorities, but like in Australia, and not just Australia, over large parts of the world, we're now facing issues of climate change, of course, you know, basically not just CO2 going up, but actually the really dangerous thing of dangerous hydrological extremes. It's dangerous hydrological extremes that kill people. Okay? It's the cyclones, the floods, the damage, the droughts, the acidification, the wildfires. All hydrological. And they're the things that kill people. We lost 5.5 million hectares of forest this summer in Australia. 26 people, 3,500 houses, thousands of agroecological enterprises up in flames. Okay, so it's hydrology that's a big thing. So really we say here is in a sense nature's simple tool. How can we use that to address some of the crises? And we won't have time today, or we can talk about it, but not that we're going to go into detail into addressing each of those problems, but let's just start with, in a sense, the issue of hydrology. How do we actually rebuild and rehydrate landscapes? And the first thing, of course, we come to is, yeah, we need bed springs, right? We need carbon. So we say, well, where do we get the carbon from? And of course, that's again no problem, because we know that there's this guy, Charles Keeling, 1958, and he gave us a graph. CO2, time, and he did this in 58, but just say by 1968, the data was totally compelling, proven, verified. And we'd started off at 280 parts per million, but basically CO2 was rising. It's now 416 parts per million, going up 10 billion tonnes of carbon every year. But of course, we see this, of course, as a problem, don't we? We see this as, yeah, this is pollution, a problem. But when we think like nature, and that's what we have to do, you know, we have to sort of change the thinking. Albert Einstein, right, he's a dude, he sort of said you can't solve a problem with the same thinking that created it. So we step outside that problem. Then you say, no, hey, this is you see this as a problem, we see it as a symptom. But better than that, we see it as a resource. And we see it as an opportunity. Because rather than just washing white lines off asphalt, we're in the business of bed springs. Right? We're in the business of bed springs. And so if we need bed springs, we need a resource, don't we? For bed springs. And of course we look at Keeling and he's gave, look, it's all there, it's been there for 50 years. And Keeling gave us that graph. You see, every year, guess what happens? We have emissions and we have drawdown from our residual biosystems on this planet. Of course, and every year we're down 10 billion tonnes carbon in deficit. And of course we've said, oh hey, we've got 8 billion tonnes of carbon per annum from fossil fuels. So we've just taken that simplistic idea, oh, if we stop all fossil fuel use, hey, we'll be okay, partly okay. And the problem is, there's 7.5 billion of us, and we haven't got 7 billion people volunteering for harikari. How unfair of them. Okay? Because we have an industrial ecology that's basically based on, energy, ridiculously excessive use of fossil fuel energy, but hey, that's where we are. We wouldn't be 7.5 billion people without it, so we've got to find smarter ways. And in a sense, Max and I, you see, that's what we were doing, because basically when we went to Paris COP21, we changed the game from, hey, it's not just that thing, it's all about zero net as targets. And the big word is net, because in a sense we gave ourselves license to play in a bigger sandpit. Not just looking at this, but saying, look, there's hang on, there we are. 130 billion tonnes of carbon per annum in emissions, and every year there's 120 billion tonnes of carbon in drawdown from residual biosystems. So hey guys, we've got 250 billion tonnes of carbon to play with to try and get to a 10 billion tonnes deficit target. Easy. Because in that 250 billion tonnes, there's extremely practical, extremely profitable, feasible options, not just to say 10 billion tonnes, but 30, 40 billion tonnes. But let's not be greedy. Basically, all we're saying is, can we do 10 billion tonnes plus another 10 billion tonnes, because that will take CO2 down again to stable levels. So have we got a 20 billion tonnes carbon per annum drawdown target that we can get to? Yes, we can, practically, profitably. We can have a discussion about the elements, the play in the sandpit to get there, the details, but it's easy. I mean, I think, like the wildfires in Australia, basically every year, 350 million hectares of forest burn, emitting from 50 to 200 tonnes of carbon per hectare. Add that up, and hey, we've got a gameplay here. We've got Pablo, we've got ecological grazing strategies, 5 billion hectares of rangelands, herbivores turning carbon, biomass into soil carbon, biofertilizer, and this waste product we call protein that we have to sell to somebody, Pablo. Okay? But the point is that there's extremely viable, valuable opportunities. But the point is it's the 20 billion tonnes, so we don't want to just go to zero net. Your Prime Minister has sort of asked, has sort of said, okay, can New Zealand lead in zero net? When can we get there? But basically we're saying easy, but we can do better. We can go to negative net. Negative net. Okay? Because that's the 20 billion tonnes. But now comes a disappointment. because even if we did 20 billion tonnes, sorry guys, it's too late. Okay? Because to do this, we haven't got the time. The oceans contain 38,000 billion tonnes of carbon, dissolved CO2 in them. The atmosphere is 750 billion tonnes of carbon. So the oceans have 50 times more carbon in them. And of course, as we reduce this atmospheric carbon level, the oceans will say, thank you very much, give a bit of a burp, not a very loud burp, and just return that CO2 back into the air. So we're here for 100 to 1,000 years plus, drawing down carbon even at negative net to try and get this CO2 level down. So again, we have to start thinking differently because, hey, we can't do that. But then again, do we need to do that? There's no question that CO2 is a greenhouse gas. It drives 4% of the global heat dynamics. We know that, 4%. But also we know that people die in submarines at 10,000 parts per million CO2. You and I breathe out air that's got 1,000 parts per million CO2. So, like we're not going to die instantly at 420.